Hello everyone, and welcome back to our series on quantum mechanics. In the last video, we looked at both the bound and scattering states of the Dirac delta and double Dirac potential wells. In this video, we will look at our next important potential well, the finite square well. The setup we will consider is described as follows. Suppose we have a potential that is 0 between x equals minus a and x equals a, and v naught everywhere else. Note that if we take v naught to plus infinity, we simply get the infinite square well, which we considered a few videos ago. However, in that video, we considered a well from x equals 0 to x equals a, while here we instead consider a well from x equals minus a to x equals a, as we can leverage symmetry to make the analysis easier. Hence, if you want to compare these results to what we got for the infinite square well, you should also recognize the fact that you need to compare this to an infinite square well of size 2a, and also shift the eigenstates accordingly. With that out of the way, let's go about actually finding the allowed energies and eigenstates. For the bound states, we can see that we cannot have E less than or equal to 0 as V is greater than or equal to 0 everywhere. Furthermore, if E is greater than V naught, the state will not be bounded by the potential, as V tends to V naught as x goes to infinity. Consequently, any bound states must have energy between 0 and V naught, so we shall constrain it as follows. As we saw in the previous lectures, if a potential is constant within a given region, we have that E less than V means that the wave function decays exponentially, while E greater than V means that we have a sinusoidal shape, or in other words, a complex exponential. Therefore, based on the constraints imposed on E and the general shape of V, we have that the wave function behaves exponentially outside the well, but is sinusoidal inside. Since the bound states must be normalizable, we have that A equals 0 and G equals 0. Furthermore, because this potential is even, we have that any bound states must be even and odd functions. For the even case, we have the following shape of the bound state. Using the continuity condition at x equals plus or minus a for psi of x and psi prime of x, we can obtain the following relation between kappa and k. Since both of these variables are functions of E, this effectively constrains the allowed energies to those that satisfy this transcendental equation. In particular, we can introduce variables z and zeta, where z is equal to k times a, and zeta is equal to the square root of k squared plus kappa squared times a, which when we then expand out in terms of E, gives us the following. We would now solve this equation graphically or numerically to find the solution z sub n, which we can then use to calculate the corresponding quantized energy levels. Note that here we index n with odd values, as we are following the same convention we used for the infinite square well, where n equals 1 denotes the ground state. Since the ground state is even and the parity of states alternates with each n, we essentially have that n equals 1, 3, etc. will correspond to the even eigenstates, and n equals 2, 4, etc. will correspond to the odd eigenstates. We can repeat this analysis for the odd case as well, using the same set of relations to get the following transcendental relationship between z and zeta, which should look quite familiar to what we developed for the even case, except we now have minus cotangent instead of just tangent. Of course, we can then solve for z sub n again here to obtain the values for n equals 2, 4, and so on and so forth. Something I've neglected to mention thus far is how the solutions to these transcendental equations actually look. If I plot the tangent and cotangent expressions we arrived at alongside the square root term given by the semicircle, we can see that there are only a finite number of intersections. This means that unlike the infinite square well, where there were an infinite number of bound states, for the finite square well, we only have a finite number of bound states. This makes sense, of course, since the potential at infinity is finite, meaning that there will be a maximum energy at which point any state with more energy will become a scattering state. You can see that the radius of the circle is guided by the size of zeta. We can then see that increasing zeta increases the radius of the circle, leading to more intersections and therefore more bound states. However, notice that regardless of how small we make zeta, we will always intersect the first tangent curve, meaning that there is always at least one bound state present irrespective of our choice of parameters. Okay, that's all well and good, but how do we know how many bound states there are in general? Well, observe that these alternating tangent and cotangent curves reach vertical asymptotes at intervals of pi over 2, meaning that if our semicircle is within a given bucket from n pi over 2 to n plus 1 times pi over 2, there is guaranteed to be an intersection. Consequently, the number of bound states is given by taking the ceiling of the radius of the semicircle divided by pi over 2, giving us the following expression. The ceiling function here simply means that we always round up, so ceiling of 3 is 3, but ceiling of 3.1 is 4, for instance. Solving for these n values of z sub n, we get the following even and odd eigenstates, with corresponding energy levels given as follows. Just as for the delta potential, I have left these b sub n constants just for normalization purposes, as it's really tedious to calculate these. Even if we can't find the allowed energies analytically in general, there are some interesting limit cases to consider. Firstly, consider what happens when v0 goes to infinity while keeping everything else constant. Since zeta squared is proportional to v0, this square root expression in our transcendental equation goes to infinity, meaning that the solution z sub n will be those for which the tangent and cotangent functions go to infinity, which occurs at z sub n equals n pi over 2. Substituting this into the general formula we described previously, we can see that the allowed energies converge to those of the infinite square well with width 2a, as we would expect. Second, consider what happens if we take a limit as a goes to 0 and v0 goes to infinity, while keeping v0 times a constant. In particular, we will define 2v0a to be the constant alpha. Since zeta is proportional to the square root of v0 times a, this quantity will go to 0, since the decay in a dominates, meaning that we only have one ground state as discussed previously. With this in mind, I'm actually going to change our potential slightly by shifting it down by v0, giving us the following. This won't change the number of bound states or their structure, but it is necessary to properly approximate the ground state energy, as otherwise the growth of v0 will dominate the smaller terms. With this shifted potential, we now have to redefine kappa and k as follows. Nevertheless, we can still use the same transcendental relation between the two quantities as follows. Substituting in the expressions for k and kappa in terms of e, v0, and a, we get the following. With some algebraic manipulation, we can get the following relation. Here, we can effectively ignore the contribution of e on the right-hand side, since e is proportional to kappa squared, and kappa will be close to 0, meaning that v0 will be much larger than e, and will dominate this term. Since we are multiplying v0 by 2a, we can substitute this for alpha to get the following. With some manipulation, we then get the following energy of the single bound state of the finite square well. As you can see, this is simply the ground state energy for the delta potential which we discussed in the previous video. Going back to the general eigenstates, let's see what these look like overlaid on the potential. Here, the dashed lines indicate the energy levels of our two bound states for this particular choice of v0. Plotting the two bound states, we can see the sinusoidal behavior inside the well and then an exponential decay outside the well. You can imagine that as v0 increases, the decay outside the well happens much quicker and the sinusoidal component becomes much stronger, giving us the infinite square well eigenstates. On the other hand, as the well gets narrower and deeper, the sinusoidal component will get squeezed out and the exponential decay terms will dominate, giving us the eigenstate for the delta potential. With our discussion on bound states concluded, let's take a look at the scattering states. Here, we have that in each region, the wave function takes the form of complex exponentials and sinusoids. We will describe the regions outside the well with complex exponentials and the region inside the well with sine and cosine for the sake of convention, since we are only concerned with amplitudes A, B, and F, which are the incident, reflected, and transmitted amplitudes respectively, and leaving the middle in terms of cosine and sine allows us to eliminate C and D more readily. We will assume a right-moving incident wave from the left, meaning that G, of course, will be 0. Using the continuity and differentiability conditions at x equals plus or minus a, we get 4 equations that we can rearrange with some tedious algebra to get the following relations between b, f, and a. Computing t equals the absolute value of f squared over the absolute value of a squared, we get the following value for the transmission coefficient as a function of e. Analyzing this expression, we can see that t equals 1 if and only if this sine term vanishes. Setting the argument of the sine function equal to n pi, we can see that the energies for perfect transmission match those of the infinite square well exactly. As we can see, the finite square well has a finite number of bound states, which seemingly resemble those of the infinite square well, particularly as the potential outside the well, V0, approaches infinity. We also observe that there is always at least one bound state present, and as the well becomes narrower and deeper, the sole eigenstate and its energy approach that of the delta potential. Furthermore, the finite square well displays some interesting scattering properties not found for its infinite counterpart. In the next video, we will wrap up our discussion of notable 1D potential wells by looking at the bouncing ball potential. I hope you enjoyed this video, and I will see you next time.